At the end of this topic, you will be able to map the magnetic field around a bar magnet, trace the magnetic field lines around a current-carrying conductor that are straight and circular.
Now look at the visual. Do you see some lines going between the poles of the magnet? Do you know what these lines denote? These lines denote a specific space or region. Let's see what this is. The space or region around a magnet in which a force is experienced by a magnetic pole is called magnetic field. Let us perform another activity to see the behavior of iron fillings in a magnetic field. Take a cardboard. Place a bar magnet at its center. Sprinkle some iron fillings on the cardboard and tap the board gently. What do you observe? We observe that all the iron fillings get aligned themselves in the direction of the magnetic field. The pattern in which these iron fillings form a line is the direction of line of force in that area. To map the magnetic lines of force, fix a sheet of paper to a drawing board. Keep a bar magnet on the sheet of paper at its center. Now, adjust the drawing board and the north pole of the bar magnet along the geographic north using a compass. Place a plotting compass near the bar magnet. With a pencil, mark the direction of the north pole of the plotting compass. Move the plotting compass in such a way that the south pole of the plotting compass is in alignment with the first point and again mark the second point. Join the first and the second point and mark the direction of deflection. By repeating this action, many more points may be obtained, and the line joining all these points is called the magnetic line of force. Hans Christian Oersted investigated the relation between electricity and magnetism. After many years of hard work, he experimentally proved the existence of magnetic field near a current-carrying conductor. In his experiment, he showed that when a current-carrying wire was kept parallel to the axis of magnetic needle, the needle was found deflected from its normal position. When current was reversed through the wire, the needle was found to deflect in the opposite direction.
We have learnt about Oersted's experiment. Let us learn that current-carrying wire behaves like a magnet. Pass an insulated wire through a cardboard hole and connect it to a battery through a key. Sprinkle iron fillings on the cardboard randomly. Close the key and gently tap the cardboard. What do you observe now? Yes, iron fillings arrange themselves into concentric circles. These concentric circular paths indicate the lines of force of magnetic field around the current-carrying wire. Hence, a current-carrying wire has magnetic field.
Let us discuss the magnetic field about current-carrying circular loop. Take a cardboard. Make 2 holes in it such that the wire passes through it to form a circular loop. Now, the circular wire is perpendicular to the cardboard. Connect the ends of the wire to the battery. Then, sprinkle iron fillings uniformly on the cardboard and gently tap the cardboard. You will observe that the iron fillings form circular loops. From the experiment, you conclude that the magnetic lines of force at the center of the current-carrying loop are almost straight lines. Near the wire are circular and form concentric circles. If the number of turns of the current-carrying wire is increased, the magnetic field also increases. In this topic, you have learned magnetic field is the space or region around a magnet in which a force is experienced by a magnetic pole. A magnetic line of force is the line joining any 2 points in a magnetic field. The number of magnetic lines of force present in a unit area is proportional to the intensity of magnetic field in that area.
The magnetic field produced by a current-carrying conductor at a given point depends directly on the current passing through it. If there is a circular coil having n turns, the field produced is n times as large as produced by a single turn.